Okay, so I will start. Hi, everyone. I'm Meenakshi. I'm a PhD student at IUCA, Pune. And today I will be presenting my work titled Modeling Observational Signatures of Jetted Agent Feedback. So in our work, we mainly focus on these two aspects. First is ionization, and second is emission and kinematics, where this emission is from the gas which has been affected by the jet gas interaction. So when we talk about the feedback from AGN, there are mainly two main modes which are considered. First is collimated jets, and second is uncollimated wide-angle winds. And most of these studies, they focus on how the jet gas interaction affect the kinematics, how it drives the outflows, and in result, but how can it affect the star formation in the system? But there is another aspect which is ionization, which can also affect the star formation. So most of the studies have not included this aspect, and however, there is some simulation studies like I have listed here. A few studies have been done like that, where they have found that studies where the galaxy has been impacted by the AGN-driven winds, the radiation is very weak in affecting the dense gas. But when you see jets as compared to the winds are very low power. Although they are wide angle, but they don't carry a large momentum. Whereas jets, they are collimated, but they possess a large momentum and can affect the gas in a different way other than the winds. And so the radiation from the central agent can also have a different effect. And that's what we have tried to explore in the first part of the study. Then in the second part, we tried to estimate how the shocked emission and the gas kinematics is affected by the jet, because there have been various observation studies which have found, as you can see in these two figures here, that the regions close to the jet have been affected by show high velocity dispersion in the IFU studies. So as you can see for the ionized gas and also for the molecular gas. And so here we have tried to perform resolved simulations of jet gas interactions and try to see what sort of implications we draw from them. Okay, so first about the first part here, we focus on both the ionization, collision ionization from the jets and also photoionization. So for collision ionization, we use the equation to find the ionized gas. And then after removing the ionized gas from the jets, we perform the radiative transfer using cloudy. And for cloudy, we constructed this SED, which is made to match with the observed SED, as you can see in these blue data points. And the luminosity of the AGN is kept similar to the jet kinetic power, that is 10 to the power 45 works per second. So these three are the simulations from Mukherjee's 2018, where my studies were performed. So the first you see the jet is, so this is the XZ plane in both of three of these simulations. In the first case, the jet is along the vertical axis, so it escapes very easily from the disk. In the second case, the jet is inclined at an angle of 45 degrees to the disk normal. That's why it takes a bit time, and later it escapes from the vertical axis, which is also the path of least resistance. And in the third case, the jet is launched almost close to the disk plane. So the angle is 70 degrees from the vertical axis. And so in this case, the jet, it remained confined in the disk till the end of the time. So these are some of the results from the first ionization study. So this is we just transformed it to spherical grid for the cloudy, to perform cloudy computations. So this is the phi equals to 0 degree plane, where you see this disk and there is a jet racer. This is the disk plane, and this is the temperature map of the dense regions. And later we removed these ionized regions using the Saha equation, and then we perform cloudy computation, where you can see that in this disk plane, the central region has been ionized by the AGN radiation, but most of the parts has been left unaffected. And in the vertical plane also, the AGN radiation can easily escape from the vertical plane, and you can see these wide ionization cones, but it is hindered by this dense gas in these two regions along the disk. Okay. And so this is just the evolution of the ionization cones for these two cases, where one case the jet is vertical, another case jet is inclined. So you can see in this case, the most of the ionization cones, they are wider. But here you will see this sum of dark rays which are forming into the ionization cone. So this sort of dark rays is either kind of crepuscular rays, which you can see also have been observed in this system IC 5063, these kind of dark rays. And we propose this kind of rays can also be due to the jet gas interaction, because the jet, while it is interacting with the this gas, it is pushing the gas above the disk plane, which is hindering the AGN addition to ionize the region. And when we studied the cumulative effect of jet and radiation, so we found, as you can see in this figure, that the effect of jet, which is shown by this red bar, it is much stronger when compared to the winds. And it's true for all these cases. So it shows that the radiation has minor effect on the ionization of dense gas, and therefore we also expect that the star formation activity will also be not much affected by the radiation when compared to the jets. And so this is the second study where we study this shocked gas emission and the kinematics of the gas affected by the jet. So these two animations, they show the evolution of the shocked flux, and this is the width for the O3 emitting gas. And so here you can see that as the jet evolves into the system, the extent of the region which is shocked heated has been enhanced. And also at later stages, we notice this S-shaped distortion morphology, which I show more clearly here. So it has been shown at the late times of the simulation, and such kind of distortion have been observed in the system, say NGC 3393. And it is believed that such kind of distortions can be due to the outflows associated with the jets, which can compress and shock hit the regions between these and these leading edges of the jet. And from this evolution of the widths, we find that as the jet evolves in the system, the extent of region, a high dispersion region increases, and it follows the path of the jet. And later we observe high widths biconical structure. So this kind of structure, we believe it is due to the outflows along the minor axis, because those are the path of least resistance for the jet, where the outflows can easily escape. And for a case where the jet is very closely inclined to the disk plane, we find that this leads to high dispersion perpendicular to the jet. And such kind of dispersion I have also found in this galaxy 5063 by Venture 2021, where the jet is very close to the disk midplane. So we are viewing the galaxy at edge on view. So it is very similar to this orientation and the IC 5063. And then later we also try to understand how the how the presence of jet can affect the symmetry of the velocity, projected velocity field of the disks. So for that, you can see here that as compared to the no jet case, in the jetted system, we find this S-shaped realignment in the velocity. And I will play this movie. So you can see that with time, the central symmetry has been broken, and there is a symmetry in the zero velocity centers in the center of in this region. So we have shown this with a simple toy model, that if we superimpose a rotating disk with the radial outflow, this can actually leads to this sort of dispersion. So it means that the jets, they are not only driving the outflows along the minor axis, but they have been also driving outflows in the disk as well, which are maybe closely radial, and which can also lead to distortion in this projected velocity map. And such kind of distortions have also found in these studies, and where it is believed that it could be due to some non-circular motions, maybe by some outflows, or could be due to some disk warps. So it is so we propose that that the effect of the outflows from the jet can also cause such kind of distortions. Okay, so this is the summary. So from our first part of the ionization, we have found that radiation can only affect the central regions of the disk, while the jet-driven shocks can spread farther out into the ISM. And we have found that radiation is very weak in affecting the dense gas. It is because the self-shielding of the dense regions prevent the radiation to propagate to large distances into them. And with the comparison for jets inclined at different angles, we found that the more inclined jets clear out and ionize the gas, which also allows the radiation, and because it makes path for the radiation to go to large distances. And from the second study of shock emission kinematics, we have found that jet-driven shocks shapes the morphology of emission in the host ISM and can also cause distorted emission morphologies, as you saw. And so we also performed this study for spherical system as well, which I have not shown here. So, and we have found that these high power jets in both of the system can cause high velocity dispersion along as well as far away from the jet. And we also found that jet ISM interaction, it provides rotational support because it boosts the angular momentum of the disk. So when it is viewed by an observer, the projected angular momentum. but it can also lead to some realignments in the symmetry of the disk velocity field. So these two studies can be found at these two papers in MNRS. So if you're interested, you can go and have a look at. So, thank you.
Well, thanks, Meenakshi. Any questions? Where is someone?
Hi.
Hi.
Yeah, I would like to ask a question. So, can your simulation predict the conditions at sub-kiloparsec scale?
Yes, so the systems we have probed, they are actually the central almost 4 kiloparsec disk. So radius is 2 into 2 kiloparsec, and the height is almost 1 kiloparsec. So this is mainly the nuclear region of the galaxies where the jet or AGN interaction will be very much significant.
Can it go below 1 kpc?
Below 1 kpc, what do you mean 1 kpc, the disk radius?
Below the extent of the jet from the central engine.
You mean the effect of the jet from the central region?
Yes, the effect of the jet at 1 kpc scale or below 1 kpc scale.
Yes, it can go, as people have found also in the like ICM or the cosmological scale studies, that because the jets have been found to develop till megaparsec scales, so it can also affect the ISM. So our study mainly focus on the ISM mainly, but it can also affect the ICM as well, and also the IGM.
Okay, the second thing is, so can your simulation tell the relative contribution of shock and the ionization?
No, actually, so there is some of caveats because this ionization studies has been done post processes, so that is also sort of drawback of the study, because if there had been AGN since the initial time, so there can also be like the outflows due to the radiation, which can also affect have more strong effect as we have found here. And also because the study is done at the post processes, so we already had a disk, but if there had been AGN active since initial time, the effect would be more stronger. So we could not actually find what is the extent of shock from the AGN here.
Thank you. Okay, one question there.
I have a question. You saw that if you inject some inclined jet, but it is immediately becoming vertical. So can you explain why? And also, what is the velocity and the injection velocity in your simulation case?
Yes. So for these jets, the gamma is around 10. So the velocity is around 0.9 or 0.8 times speed of light. And so this is happening because the jet here, it is trying to push the gas in these directions. However, it is being hindered by these dense regions. But here you can see that the jet is trying to make some channels, some small channels into the disk, as you can see here. But however, the channel along the vertical axis, it will escape out more easily, and that's why at later times the jet just shifted its path along the vertical. So there will be some small channels into the disk which will still be continuing, but the main channel, it will just shift towards the vertical, because along the vertical there is not much resistance. The density is less as compared to if it goes into the disk.
So, yeah, just a quick question. Did you check the resolution test for these simulations? Because if you have a low resolution, you can get this type of feature. Like we are getting the same, so that's why I'm asking. So did you check the resolution?
Okay. Yes. One can do that. So here these simulations are around actually 6 parsecs. This is the regional element, and the size of the cloud is almost 100 parsecs. So it's like we are actually resolving it more than 10 cells. But yes, one can go for also better resolution to check if there is some effect.
Okay.
Long live India and France friendship.